Okay, we will see. Okay, the lessons is regarding, as I said by Giuseppe, regarding the material screening. First principle only, I will not go into details, and the reason for first principle and not details comes from the fact that I am not an expert of material screening. That is, so this is the main reason. I am only a pedestrian and a simple user and not a real expert in this so delicate topics. That is the reason. Okay, what I will attempt to say is the reason to do material screening, but this in partially is well understood because we are doing experiment in which it is fundamental to have a very low number of background events. I will briefly describe how it is done, the material screening. I will introduce the two methodology, main methodology, so the measurement of concentration and measurement of activity. Then I will say something regarding a mysterious fact, which is the breaking of the secular equilibrium. Then I will compare the sensitivity of the different techniques, and then I will end up saying something more regarding the specific technique, so gamma spectroscopy, mass spectrometry, neutron activation analysis, and then alpha spectroscopy. All the material comes from slides presented by expert, the real expert, Nisi, Pagnanini, and Monica Sisti. These slides were talks and were presented during dedicated school and also dedicated talk in specialized conference. This one, LRT, is a low radioactivity techniques conference dedicated to the material screening and all the activity around the low radioactivity business. So the interested person can give a look to this series of conferences in which there is a large amount of material, of interesting material. So this is the outline. Said this, why we have a necessity of a material screening. But the reason, as I said, now after 2 weeks, we think we have all understood. We are interested in a process very rare, in which at the end, if we are lucky, we will end up with a bunch of events. Here I am written 10 events because I am at the end of a story very optimistic, but maybe even less. And what we have learned also, you have to take data for many years, of the order of 10 years, in order to have high sensitivity. From there, connected with the fact that you, at the end of all this time, you have a very small bunch of events. This is due to the fact that the cross-section is very low, both because you are searching dark matter or you are searching particular interaction of a neutrino, or in case of a neutrinoless double beta decay, the half-life is very long. So all this means that not only very long time of data taken, but also experiment with a huge mass. We are talking now of the next generation are dealing with ton scale experiments. In many cases, also in order to protect the experiment from the environmental radioactivity background, there are also massive shielding in some case, so in order to protect from the gamma, from neutrons and the muons, and for each of these radiation you have a dedicated material, lead, copper for the photoradiation. For neutrons it's better to use water or polyethylene doped with boron or gallium or whatever, and the muons it's better to have active veto. Anywhere, the large mass of the detector plus also the shielding, you have a large amount of different material. So this is the situation, and the question is what happens if we do not select the material, we don't do anything special. So the situation can be understood from this example. For example, you buy a commercial crystal, 1 cubic centimeter of lead tungstate. You can have a cryogenic, you can realize a cryogenic calorimeter, and you take data. What you observe is more or less this type of result. The scale is 1 volt per division, and here you have 10 seconds. You see that you have a huge amount of signal coming from the material itself, because the material itself, if you don't do anything, contain a large amount of isotope which decays. And if you do a calculation here, you see that if you don't do, you have easily a high rate, a trigger rate. Here you can, in this case, you have 3 hertz without background events. So in this, if you stay in this situation, of course, you understand very well that you can do anything. So this is not a detector for searching rare events. What changes if you instead you select, so you build this crystal, this detector using raw material clean, so selected, and also the building of this detector is made following dedicated procedure in order don't contaminate the material itself and its surfaces. Here is the situation in case you have the same detector, lead tungstate, but here also you have the dimension is bigger, 100 cubic centimeter, using this selected material for building the detector, and you see the situation in this one. Of course, pay attention to the different, so here is 3 volts, minus 3 volts, minus 3.2, and you see here is the situation. Now, you see that this is only, there are no more pulses. It's possible to do physics of our type with this detector, because you don't have more this contamination of material of your detector. With this type of selection, you are able to make the physics that you want to do. Okay, why you have this situation? The answer is simple, due to the fact that the material with which you build the detector contain typically uranium, thorium, and potassium. Here you see the chain of the uranium 238 or the chain of thorium 232. In blue, I have singled out the primordial parents, so the origin of this decay chain. In green, the gamma emitter, the various gamma emitters in this chain, and in red, the alpha emitters. So the reason for what we have seen with the unselected detector is unselected material for the detector is due to the presence in the material of this chain. Okay. So, as you can easily understand, when you build a material, a detector for this type of very rare process, what is done is to increase the cleanliness when you go near the detector. So the structure is some sort of onion in which the material are less pure, radioactive pure in the far away from your detector, and going inside in your detector, the quality of the material has to be more and more clean. There is also the fact, but this is due to the type of interaction that we have with of the alpha, beta, and gamma with the material, that material, when you think, you realize your detector, material, the material near the detector, you have to pay attention to alpha, both to alpha, beta, and gamma, background. When you think to material far away from your detector, what is important is only the photon background, gamma background, due to the different interaction that this particle has with the material. Okay. So now, this is more or less the reason and the general aspect of this type of material. And now, what remains to understand is in which manner it is possible to quantify the contamination. And in order to quantify the contamination in a given sample of a material, there are two main ways. The first is to measure the atom concentration, and the other is to make a activity measurement. The choice of atom counting or decay counting depends on the decay constant, mean lifetime, half-life, what you want, or the isotope that you want to understand, the presence. The sensitivity, the ability of your instrumentation to see this material, contamination, sorry, and the measurement time. So, another point, another interesting point is that very often the characterization of material is quantified with what is called the specific activity. The specific activity is given by the activity that you have measured divided by the mass of the material, so is given in becquerel per kilogram. Okay, there is a formula which connect the activity with the concentration. The specific activity, as I said, is given becquerel per kilogram, while the concentration is given in gram per gram, in percentage. The relationship between these two quantities, to go from one to the other, is given by this formula. Here we have the becquerel per kilogram, so the activity, and here is the transformation in gram per gram. So in this is the activity, specific activity, and this is the conservation, the concentration. Tau is mean lifetime of the contamination that you are analyzing. Na is the Avogadro's number, and mm is the molar mass. If you do this calculation, there are this, you do this calculation of the various contaminant, you end up with this transformation rules in which if you have an activity of thorium-232 of 1 becquerel per kilogram, using this formula, you end up that this is equivalent to a concentration of 246 ppb. For the billions. Okay, is ppb is a 10 to minus 9. Okay, and here I have put, and uranium 238, you do the same calculation, you obtain. These are thorium, uranium, and potassium, as I said, are natural isotopes. They are they are natural. They are there due to the life of our Earth, and then there are also contaminants, isotope contaminants, which are not origin from the natural process, but are due to anthropogenic human activity. Cobalt 60. If you do, is so the transformation is correct because this is what is you extract this transformation, say what is the concentration of, for example, uranium or thorium, which produce 1 becquerel per kilogram. So if you bring the this formula, for example, this one, you start from this formula, you extract the number of particle which you see, so what is decay, so is N0 minus NT. You assume that the time that you measure is very low respect to tau, so you do so you can see this expansion, and you obtain, then you divide by the, and you obtain. This formula has this meaning. So if you have an activity of, you obtain this, it comes from this concentration, or vice versa, you can do, if I have a concentration of 1 gram per gram, what is the activity? But is correct. No. So if you do this in this manner, is really correct. I have done exactly the calculation. I can send it to you. At least this is the meaning of the formula. But it's a good exercise because I have had the same the same problem. Okay, given a look to the decay chain, this is for the you don't see very well, but it's not a very good slide. But anyway, this is the same chain that I have shown before, only with more more information, both for the uranium-238 and but you can do in 2 directions. This is activity, and you. But we can discuss them, but okay. Anyway, if you assume this true, you end up with this formula. Okay, with these numbers. Okay. Okay. Okay, and so these are the decay chain of thorium and uranium with more information. Regarding, return back to how we are able to measure and adopt the all concentration or activity, the concentration are mainly dedicated to the primordial nucleus, while the activity, so the decay, is for other part of the decay chain. Okay. Usually, if there are everything happens in a normal manner, so if we do, for example, the analysis of the concentration of uranium or thorium, so the primordial, if this chain is perfectly follow, you are able to follow to understand what is a contamination coming from all the sands of this of the chains. And this is the assumption that this chain of decay is in secular equilibrium. So there nothing happened to disturb the chain. Unfortunately, many often, this secular equilibrium is broken. And is broken due to two actors, the radium and the radon. So these guys here. Radium. Radium is components very active from the chemical point of view. So it react with the water, for example, and so you easily can eliminate from the chain. So the chain is broken, and so if you know the concentration of the primordial, you don't know more what happens for the other part of the chain. And so this means that knowing the concentration of the primordial is only a part of the information. So you can be in trouble, for example, for other other contaminants of this chain. The other actor which breaks this secular equilibrium is the radon. Radon is a noble gas, so escape easily from your material. And so also radon is something that can break easily this chain of decay. So you have also taken into account this when you establish the material contamination. Okay, so now more or less we know everything, or we assume to know everything. What are the methods in order to understand the contamination, and what are their sensitivity? So there are more than one method or technique, sorry, in order to measure the radioactivity of material. We have germanium spectroscopy, radon emanation assay, neutron activation, liquid scintillation counting, mass spectroscopy. There are a lot of different techniques for the mass spectroscopy, and alpha spectroscopy. Germanium spectroscopy is dedicated to the search of photons, or photon nucleus which decay in photon, of course, due to the fact that the germanium has a powerful energy resolution, is the detector for the photons. The sensitivity of germanium spectroscopy for uranium and thorium is of this order, 10 to 100 microbecquerel per kilogram. This is the typical for this specialized laboratory. Don't reach this sensitivity if you don't do spatial arrangement, of course. This is the status of the art. Radon emanation, of course, is sensitive to the radon and the other part of the thorium chain, and the sensitivity is of this in this range. Neutron activation, which means that you use a source of neutron, you excite the neutron is captured by a nucleus, and the nucleus is remain in a state excited and then decay. This technique is sensitive to the primordial parents of the higher part of the chain, and here is its sensitivity. The liquid scintillation is mainly used for alpha and beta, for the search of alpha emitters, due to the fact that if you analyze the shape of the signal of a liquid scintillator, making a pie-shape discrimination, you are able to distinguish between alpha and beta particles. And here is its sensitivity. Mass spectrometer is a very powerful method in order to know the concentration of the primordial parents. And you see here what is the sensitivity. And the alpha spectroscopy, of course, is for the alpha emitting particles. Here, instead to have the usual specific activity in becquerel per kilogram, here the sensitivity is given in becquerel per square centimeter, of course, because alpha you can see alpha, detect alpha, or contaminate alpha only on the surface of the material, and so this is the correct dimension, or correct quantity in some sense. Then we will check better what is the different aspect. We compare the various aspects of this technique. But going back to the problem of the secular equilibrium, the germanium spectroscopy is the right manner in order to control the secular equilibrium, because being sensitive to the photon emitter, you can check the various emitters, and so you can compare the intensity of a different gamma peak and control if the secular equilibrium is preserved or not. You don't have many other knobs in order to see if your material is the contamination is correct. So if you want to do a good job in the material screening, it is important, for example, to make, for example, a mass spectrometry analysis, which gives to you the primordial parents contamination. But if you want also to know if everything is follow the secular equilibrium or not, you have also to do a germanium spectroscopy.
In other words, with the germanium spectroscopy, you're saying you're comparing the relative amplitudes of gammas before and after you get to radium or radon.
Yes, exactly. So you see what is the reality, and from this comparison, you understand if the of course, take into account, of course, the acceptance of your detector, blah, blah, blah. Of course, this is from Monte Carlo, you know, the efficiency and so on. But if assuming that you have done the correct, all the correct analysis, and you have correct your data, comparing the various peak, you see that if the secular equilibrium is preserved or not. And so you know what is the situation for all the pieces of your decay chain. This is. Okay. So now I put here some specific consideration comparing these four main techniques. Neutron mass spectroscopy and neutron activation are two activity from which you measure the concentration, while the gamma spectroscopy and the alpha spectroscopy, the activity. Okay. Regarding the sample that you can analyze, for the mass spectroscopy, you can use liquids or solid, which you dissolve in liquids. For neutron activation, you can work with the sample both in a solid or liquid state. For the photo spectroscopy, your sample can be solid or liquids, and the alpha spectroscopy is has a different approach. It is sensitive to the surface contamination. So, to which contaminants these different techniques are sensitive? As I said, mass spectroscopy is sensitive to the primordial isotopes and also the neutron activation, while the photon spectroscopy are sensitive, as I said, to photon emitters, and alpha spectroscopy in effect is sensitive to the large part of the radioactive chain, because as we have seen, this radioactive chain contain many alpha emitters. Of course, now you have to be sensitive to have a sensibility to the various different peak of alpha, which is not easy, because easily the alpha interacts with the matter, and so you have degraded alpha, which spoil your sensitivity, ability to distinguish one peak to the other. Is difficult. How large? What is the mass of the sample that you are analyzing? That is a necessity to use in these techniques. For the mass spectroscopy and also for the neutron activation, it is not necessary to have a large mass. For the mass spectroscopy, it is enough to have some gram. And also for the neutron activation, you don't have necessity of a large mass, tens of grams only, and you have your result. Instead, to have a high sensitivity using the photo spectroscopy, you have to use a large amount of material, few kilograms or tens of kilograms, in order to have a good sensitivity. For the alpha spectroscopy, maybe it's not necessarily large mass. Okay. Then another factor is how long you have to measure, because you understand the mass and the time are two knobs in order to increase the sensitivity of this measurement. The mass spectroscopy is very fast, very fast techniques. Between the preparation and the measurement and the analysis, a few days. The neutron activation, also here there is the preparation of the sample, then you put your sample under a large flux of neutron, and then you analyze the reaction of the nucleus to the neutron capture. Few weeks, we can say. For the photon spectroscopy, here you have to reach high sensitivity. You have to use large mass, as I said, but also a long time period, many weeks, months, okay? And the same is for the alpha spectroscopy. These are mature or not mature techniques, depends. For example, ICP-MS, so mass spectroscopy is a technique under fast evolution in the market. You see many tools, many machines able to do the mass spectroscopy. Also, the neutron activation now is improving and developing very fast, especially, of course, in order to improve the sensitivity. Photon spectroscopy is a well-established techniques because use germanium detectors. Germanium detector is a technique well-established, so is something that is well-established. What you have to improve is the material around the germanium detector. And also the alpha spectroscopy, more or less, is at the same level of the photon spectroscopy. Okay, now we have complete this overview and comparison of the different techniques. And now we can spend some time for the different for the four different techniques, so the gamma spectroscopy, alpha spectroscopy, neutron activation, and mass spectroscopy. Gamma spectroscopy. So we know that the emission of the gamma is due to the to internal nuclear reaction. The emission of gamma is very often associated also with other emission, alpha or beta decays. The emission of this gamma from the various from the nuclear structure is a very fast process, and so due to this very fast process, it is very easy to single out the author of this transition. And so you can single out single out the origin. So, for example, cobalt. You know that cobalt. You see the presence of cobalt 60 from two gamma line of 1.1, 1.3, and 1.3 roughly mega electron volt. These are due to the fact that the cobalt beta decay into nickel 60, and the nickel 60 immediately has a too strong line at 1.1 and 1.3 mega electron volt. And if you see these two, you know that you have a cobalt 60. Okay, that is. There are, well, recognized that there are specific features in this gamma spectroscopy, in this gamma ray. The gamma have a well-defined energy, so there are no questions. As I said, they characterize the decay in a very non-ambiguous manner. You have also possibility to have a cascade, so more than one type of a peak. And also the branching ratio usually is very well established. So this means that you can calculate very well the intensity. Okay, so now we go to what one of these gamma spectroscopy setup measure. So with a gamma spectroscopy, you measure the specific activity given background per kilogram. And you measure this, of course, you put your sample in front of a germanium detector, and you take data for a certain amount of period. We have your energy spectrum with various peaks, and for the various peak, you measure the specific activity. Specific activity which is given by this formula, trivial, if you want, in which in the numerator you have the difference between the counts coming from when you have the sample, minus the counts if you don't put the sample, if you want. And here you have in the numerator the right, the correct number of counts coming, decay coming from the your sample. In the denominator, there is this product of the mass of a sample, the time that you spent during the measurement, the time of the measurement has to take care of the dead time of your measurement, so is the real time minus the dead time. You have to take BR is the branching ratio, and epsilon is the total efficiency acceptance of the measurement. This efficiency of the measurement, as usual, comes from the knowledge of the characteristic of your setup, of your detector, and is obtained usually thanks to Monte Carlo simulation. Okay. So you understand, in order to have a good or an excellent sensitivity to this quantity, what is necessary? It is necessary to reduce the counts per background, of coming from the background, and you have increase the product of the mass of your sample, the time of measurement, and the efficiency, of course. Okay, if you do this, you increase your sensitivity. Easy to say, but is not so easy to realize in the real world. The reason is that the quantity that I have talking about in the previous slide have a strong correlation. In the sense, if you increase, if you increase the mass of your sample, you decrease the efficiency because there is auto-screening of your sample, for example. So you have to pay attention. If you increase the time of measurement, also the counts of the background increase. Okay, so you have to pay attention to all these factors in order to increase the sensitivity. In other words, it is mandatory. First of all, reduce the radioactivity background. This is the main issue, the main point. And what you can do is selecting another time radio pure detector components. So your setup, in which you do the germanium spectroscopy, has to be built with very clean material. It's trivial to say, but is an ingredient, an important ingredient. Then you have to shield the detector. So typically, if you want to push the sensitivity of germanium spectroscopy, but also for other measurement, for example, you have to do this, so you have to build this setup underground, for example, in order to reduce the flux of the cosmic ray, for example. So, or you have to put active shielding and passive shielding in order to reduce anyway the background. Okay, and you have to wait to the muons, of course, if you are above ground. Of course. And then the other is to maximize the product of efficiency multiply the sample mass. So you have to optimize the shape of your sample in order to match the geometry of your germanium and the relative position, and then you have to work with Monte Carlo simulation in order to find the best setup. And of course, the experience here plays a major role, of course. Okay, and anyway, the first important issue is the background reduction. Okay. So, example of this setup. Here I put the GEMPI, which is a spectrometer, germanium spectrometer, that works at Gran Sasso, underground, in the underground laboratory. It was built many years ago, as you see, and it was realized and put by the Max Planck of Heidelberg. The setup, so the core of this setup is this germanium detector. Inside a strong screening, a powerful screening of copper electroformed, so very pure, and put soon after the production of this copper underground, in order to don't see too much cosmic ray, and so have the contamination. Around the copper, there are a massive shield of pure lead and so on. Okay, this is GEMPI, I think, remain the status of the art, or one of the best germanium detector for this type of measurement. And the region where you put your sample, this one is 15 liter of available, of volume available for the sample. Okay. Oops. Of course, this is the germanium screening, or this type of measurement is, you can say, a small industry. We have, for example, remaining in Italy, in Gran Sasso, there is a laboratory dedicated to this type of measurement called Stella. I don't know now what is with the new name, but up to now, this is the name of this laboratory, which contains not only one germanium detector, but many germanium detectors, so you can do in parallel many screening. Here you see a view of this laboratory. Here there are the various screening, germanium screening facility or station, and here you see how it looks like the volume for this type of measurement. Here you have of the order more than 10 germanium installed. They are, as I said, shielded with a passive layer of copper and lead, and also the entire setup is fluxed with nitrogen or other flux in order to reduce the radon contamination. But there is not only germanium spectroscopy at Gran Sasso. There are other laboratory which has this type of facility. Here there is a list, and you can see our laboratory all around the world, and you see the crystal and the germanium system. Something are working, something are not, but anyway, you see that there is a large distributed network able with different, of course, sensitivity to do this job in the world. Okay, this is the end of germanium spectroscopy. What about the mass spectrometry or spectroscopy? In order to do this, the measurement, in this case, you have to introduce in the introduction system your sample, so you have to prepare your sample. The sample is ionized thanks to an ion source. Then these ions are introduced in a mass analyzer, and then there is a detector which analyzes the result from the mass analyzer. The result is more or less this one, as here is the various intensity of the various ions that the mass analyzer has analyzed as a function of a ratio between the mass of the ion divided by ion charge, and here you have this various peak. This plot I have extract from the web is for some organic molecules, but the techniques is very is used in many different fields, not only in the fields for the mass screening, of course. And from this measurement, you can have qualitative info, semi-quantitative, or quantitative information. Okay. So the mass spectrometry is a long story starting from the 20s of last century. The father is Aston, an English physicist, and the idea is very simple. You have an ion source, maybe it's better to collimate the beam of ions. You have a selector, in this case is a simple magnet, so a mass analyzer, and then you have a detector. In the case of the 20s, it was a fluorescent screen in which you see the impact of your charged particle ions on the screen. This is the simple philosophy. In case of a typical mass spectroscopy used in the usually used, but it is not only this one, but is the mainly used. What is used in our field is this inductively coupled plasma mass spectrometry, so ICP-MS. This is the typical, very often used mass spectroscopy used in our field, in which you have a flow of argon plus your sample, and this sample of argon, which is the carrier plus the flux of your atom of your material, are ionized thanks to this radio frequency induction coils, which produce a plasma and so a ionized flow of atoms and ions. Okay. And okay, and then this flow of ionized particles are sent to the analyzer, to the magnets system, or magnet plus electric fields, in order to discriminate the various components of your of your flow in mass divided by charge. In order to have a very sensitive result, so-called ultra trace, in which you are able to measure, to have a sensitivity of 1 ppt, so 10 to minus 12 gram per gram, so a concentration of this level, you have to pay attention to various phases of your measurement. First of all, you have to pay attention to the sample preparation. Then you have to have an instrumentation able to reach high sensitivity, and then also a clean chemistry, because in the sample in the sample preparation you have to be very careful in the preparation of the sample. And as you can see, everything has to be done in a clean environment, so in a clean room of high quality. Otherwise, you spoil very soon the results. There are, as I said, many techniques, and the remaining, or many techniques for example, remaining in the ICP-MS field. There are many devices. For example, there are the quadruple mass analyzer, in which here there are a quadruple which are used as mass analyzer, or this double focusing analyzer in which you use a magnet and also an electrostatic analyzer in order to separate the various components. Okay, this is more or less for the ICP, so mass spectrometry. Neutron activation. The basic principles are the following. You have your target, your sample. There is a neutron which hits your target. The neutron is captured, and you remain with a nucleus which is in an excited state. The excited state, the nucleus in an excited state attempt to go in a better stable condition and emits prompt gamma radiation. And then follow other process in a later time in order to arrive to in a better stable condition. So you have also beta decay and gamma decay later in a later time. So this is more or less the chain of what happens if if a nucleus is absorbed in a rough manner. Given this various steps, you can do various type of measurement. For example, if you are able to measure the prompt radiation, which is emitted in a very short time, you have so-called the prompt gamma analysis. So you measure essentially when you are activating the material. And then you have a second possibility. So you don't measure this prompt gamma emission, but you study the delayed gamma emission. And usually this second strategy of measurement is what is usually mainly done. So you irradiate, then you with a neutron, then you bring your sample and you put in a, for example, in a gamma spectroscopy setup, and you measure the delay gamma emission. And then you do your analysis. Okay. What are the possible neutron sources? Because this is crucial for this type of measurement. So you have many possibilities. There are radioisotopic neutron sources. For example, you have americium beryllium, strontium beryllium, in which there is the americium, which produce alpha, and then captured by beryllium, and the beryllium with having reacted with the alpha emits neutron. And then there are remaining on the nuclear of neutron sources. You have, for example, californium, which is a strong neutron emitter. Of course, the spectrum, the energy spectrum of these sources is different. You have to take into account when you do the measurement. You have there are also neutron generators of different energy, 2.4 mega electron volt neutrons, thanks to this reaction, or if you use this different reaction, you can reach higher neutron energy. Or you can use spallation neutron sources. So you should have a proton beam of high energy hitting a target made of heavy target. In this inelastic collision, you produce a lot of things, and but also many neutrons, and you select these neutrons in order to make your measurement. Finally, there are the neutrons coming from the decay of the fuel of a nuclear reactor. This is the technique using the neutron coming from the nuclear neutron reactor is one of the most used neutrons. One use research nuclear reactor, in which the power is of order 20 kilowatt to 10 megawatt, so small reactor for research, in which you can also use this neutron instead to produce thermal energy. You can use for other necessity, in this case measurement necessity. This research reactor produce a lot of neutron, 10 to 11 to 10 to 14 neutrons square centimeter second. And the most interesting neutrons are those called epithermal or thermal. Here you see the flux of neutron produced by a reactor moderated with water. Here there is the energy, and this type of neutron is what they are used usually in this type of activation analysis. Of course, you have, when you think to this measurement, you have to take into account also, in order to establish the time of measurement, you have to understand what is the flux of neutrons and also the cross-section of neutron capture. Here you see, for example, the cross-section for the actinides as a function of the neutron energy. Here I put some result that is possible to achieve with this technique. This technique is very sensitive to the primordial part of the primordial parents of this decay chain. Here you see the sensitivity, which are of the order of a picogram su gram, for various material used in the various experiments, for snow acrylic, for the borexino liquid scintillator for Camlan, for part of a EXO 200 detector. So these are for example, for double beta decay experiment, for the Teflon using in Majorana, another experiment, double beta decay experiment. So, and here you can judge what is able to do this technique, the sensitivity of this technique. Okay.
I just don't understand why some samples are measured with a sensitivity which is not the same than others. For example, why do you set the limit, an upper limit of 10 to the minus 5 for the borexino liquid scintillator, or you measured 10 to the minus 2 for the Majorana Teflon, but then you only have measurement of less than 7 for uranium for the EXO heat transfer fluid. So why do the limits vary so much?
But there are many sources to produce this type of measurement. First of all, the contamination of your sample, the nature of your sample. In this case, you see that this sample are a huge contamination in potassium, so you see the signal because you have a strong contamination. For the other, for example, why you are able to achieve this, here, of course, depends on the technique that you have used for the preparation of a sample, and then after that, in which manner you have measured the sample. So in which manner you have done really the measurement. So this is a field in a strong evolution, and the sensitivity can be pushed below this, strongly below this this reference of this unit, thanks to dedicated improvement in the detection. So no. These are completely different results from different neutron sources, from different laboratory. So it's not an homogeneous sample of measurement. It's only to give to us the idea of what is measured. For example, in order to measure the liquid scintillator of the contamination of the liquid scintillator of Juno. Juno is an experiment in China for which will use the electron antineutrino coming from reactors, and is made of a huge 20 kiloton of liquid scintillator. And the aim is to measure, to arrive to a measurement of a neutrino hierarchy. But this main goal can be also enriched if the purity of the scintillator is very, very high. For example, one can study the geoneutrinos of the neutrino coming from the sun. But in this case, you have to push the purity, the concentration, the purity of your liquid scintillator very, very, very far, much better than, for example, the result, or comparable at least to the result of a Berezino liquid scintillator. So in order to achieve this very demanding sensitivity, for example, you can't rely on with a so-called standard technique. You have to invent a new technique, to measurement technique, after you have activate with a neutron absorption your sample. For example, you have to push the sensitivity, for example, to use coincidence gamma electrons in order to reduce the background strongly and enhance your sensitivity. So if you want to push this technique at this level, because this is the necessity, the necessity of your detector, you have to improve respect to the standard, usual technique, your technique. You have to improve. And of course, the necessity to, all the experiments now are going to higher and higher sensitivity, which means that they have a necessity of a material purer. But this means that also your technique has to improve, otherwise you are not able to reach what you want. And there is evolution in this. For example, I have, in order to complete the answer here, I have attempted to capture this evolution, saying that, for example, for example, here, techniques under development for low-level concentration for the neutron activation is exactly what I have attempted to explain, that you have, so you activate the material, but you have to push the detection technique, inventing manner in order to be much more sensitive with a trivial gamma spectroscopy. You have to do, for example, coincidence, gamma electron, and so on. But this is really the art of the techniques. Okay, so we arrive to this table, which show more or less what is possible to achieve. And then last, but not least, the alpha spectroscopy. So here, the problem is to understand the contamination of the surface of the material. Because if you have a large surface, they are prone to be easily contaminated by radon, for example. So you have to pay attention, and it is a difficult problem to maintain clean the surface of a material. An example, very important, of the weight of the surface contamination can come from quarry. Here you see the energy spectrum of quarry, the last spectrum, I suppose, with more than 2 tons kilogram per year of exposure. This was shown in the last neutrino conference of this June. And you see the spectrum. Here is the Q beta beta. In blue, the spectrum after the base cut, anti-coincidence between different crystals, and then applying what they call pulse shape discrimination. What remains is the green part. And you see that there are various peak contaminants, but what I want to say is that this detector, for example, are the background at the Q beta beta of this experiment is dominated by the alpha contamination. Because the bolometers of quarry are detectors which are fully active also in the surface. These are not protected by construction, as for example germanium are protected because they are for example the N+ contact, which is a thick dead layer which is protect for the alpha contamination. Here instead, these bolometers are fully active, and also if you have an alpha coming from a material around in vacuum, they can produce a signal. If you are not able to discriminate, to see, well, this signal comes from a background events, you have your. This is the reason for the Cupid program, in which there is the possibility to discriminate from beta and gamma and alpha. Okay, but here you can see that alpha contamination can be a problem, for example, for this detector, and you have to change or protect from the alpha contamination or find an active manner in order to reduce the contamination. Okay. Alpha spectroscopy, also here there is a various technique. For example, if you want to screen for alpha contamination a very small surface of the order 5 multiplied by 5 square centimeters, so very thin, very small, you can use commercial detectors, for example this one, in which this one is the detector is a silicon barrier detector, so is a PN junction in which this part, which is the the cathode part is very thin in order to don't spoil, to permit the alpha measurement, otherwise you kill the alpha. And this is the small chamber in which you put your sample, and you see this is a NIM crate, so you understand the dimension of this simple device for small samples. You can also, there are also commercial detectors for large samples. This is, for example, this device is able to measure surface of this dimension, and the sensitivity to polonium-210 is of 10 nanobecquerel per square centimeter. No. This is a detector that you will see in Krakow. Okay, better. Okay, okay, and finally. Detect.
So you allow the alpha to get in and deposit energy, but you will also get some background from
But yeah, yes, but alpha are at a very high energy. So above natural gamma is at 2.6 MeV coming from the thallium above, or you have some summed gamma coming from the sum of, but otherwise you are completely dominated by alpha.
So essentially, you look just at the amplitude of your electric signal from the
And of course, if you want to be, you want to do the things in the right manner, you have to take also data without the sample in order to, this is trivial, but.
If I understand correctly, silicon is used here because it can be put super close to the sample so that you actually can get the alpha before
Yeah.
it gets.
Otherwise, also the air destroy. No, you have to make less material that you can, otherwise the alpha lose energy very quickly and very efficiently. So you don't see a problem of this alpha spectroscopy is to see the various peak because is a very otherwise you see only a continuum. So the various alpha peak are near one to the other, so it's not an easy task. No? Okay. Another point before is also the time for the measuring, which is of the order of 30 days or even more, depending of course on of what you want to, on the status of your sample and sensitivity that you want to achieve. But you can do even more. For example, remaining in the alpha spectroscopy, for example, you can use the fact that you have bismuth and polonium, in which one decay the bismuth in beta, and then you have a subsequent polonium alpha decay. There is a time correlation, strict time correlation between these two decay, and you can use this time correlation if you have a possibility to detect the beta and the alpha, and so you can check the contamination of this part of a decay chain. For example, this is an ad hoc detector built at LSC, which means Modane, if I am not wrong, in France. The sample size can be of very large surface, and the detector you see is not a small detector, and has this good sensitivity, but the measuring time is months. It's not something that you can obtain a very small time. To conclude, so we have discussed various techniques in order to screen your material. And so from this process, you can say, well, I can build my detector with this material obtained by this firm. Perfect. Okay. Unfortunately, this is only the first part of the job. Unfortunately, because there are other points, other steps, very, very important. If you fail on one of these steps, you are dead. Okay, so you have to. This is what we have described is only the first step, and not the last step. So first of all, you have to be sure of the material consistency. If you have to buy a lot of material, you have a screen a sample, but you have to be sure that all your material has to be with the same contamination, with the same property. And so here you have to talk with the vendor in order to have the entire quantity coming from the same batch that you have checked, for example. Or you have to convince the vendor to maintain the quality the quality of the production at the same level in order to have the same material, the same quantity. Then, if you have to work with the material, with the raw material that you have selected, also this part, the machining, has to be done following strict rule in order to don't recontaminate the surface of your material. So you have to pay attention. Yesterday, JJ said that for the copper of the internal next 100, they have chosen not to machine, but to use the raw bar, in order through the machine don't contaminate the copper. Then, if you have to maintain to storage your material, you have to be sure that remaining in storage, there is no surface contamination. So you have to protect the surface with some material in order that the radon can decay on the surface, produce contaminants on the surface. And as a last point, you have to pay attention of the cleanliness of the surface, and so you have at the end of the story also clean anyway your surface after the installation of the material. So, and you have, of course, make a protocol for each of these steps in order to follow strictly the protocol in order to prevent any mistake, because any mistake can spoil a kill your effort.